Hey guys, we are Team 21 and here's our final presentation. So we're going to get started with a quick system description. Our project revolves around the creation of a tube and fin heat exchanger for small electronic devices. We broke the system down into three subsystems, which are pictured here in the flow diagram. Fluid flow convection from a cost perspective, convection heat transfer based on fin geometry, and a cost analysis in regards to transportation. The shared variables amongst these subsystems primarily relate to the size and material of the device, along with the effectiveness of heat transfer through each method. The system boundary is defined around the heat exchanger, encompassing the heat input from the electronic device, the fluid flow carrying heat away, and the external environment dissipating heat from the fins. The rationale stems from optimizing both heat transfer and cost in order to make the most efficient device possible.
Next up, we're going to talk about our optimization model here. Here's a hierarchical decomposition of transportation and heat transfer system here. We have the two lower level subsystems, which are fin geometry and fluid convection, leading all into the transportation system subsystem, which is giving a profit, which we have a target profit set, and we're adjusting that. We're taking that response and adjusting our two lower level subsystems accordingly. And we'll talk a little bit about this more in detail later. For now, here's a breakdown. We have our transportation subsystem. We have our profit target that we're setting, and our response, which is our observed profit. Design variables are going to be L-fin and D-pipe, which are outputs from the lower two subsystems, which have local design variables, L-fin, N-fin, T-fin, V-fluid, and D-pipe. And our response to that is categorized here by this L-fin star and D-pipe star. And our design variables up top are for the whole system. Our ATC objective function consists of three terms, basically one for each subsystem. We have weights associated with the geometry and convection subsystems, just to tune those. And basically what each phi function is doing is trying to minimize the target to response variables. More mathematically explained here, we're trying to minimize the ATC function, which we just plugged in everything up top. And then we're going to be subject to the constraints of heat transfer, which we're going to develop as a surrogate model a little bit later. We also set profit equal to this term here, which is based off of two terms, revenue and cost of carbon emissions that are based off of L-fin and D-pipe. And we just set each of the terms for one for this example. A theoretical format explained here is just here. And our objective constraint trade-off, the objective seeks to primarily optimize profit, especially given the weights that can be tuned for L-fin and D-pipe. The weights being lower would put a lower emphasis on the heat transfer constraint. So the company can choose to optimize more profit at the cost of the quality of the product, but that's not necessarily recommended. And that can even be flip-flopped if you want to.
So this table hopes to review some of the differences in system level optimization versus subsystem level optimization. So first, at the system level, the primary goal is simply to optimize profitability while balancing and ensuring heat transfer parameters are still met. At the subsystem level, each design variable is optimized locally and then passed along to the final subsystem, which creates suboptimal performance from a broader perspective. Additionally, at the system level, the weighting of the design variables is malleable, various variables are backpropagated, and heat transfer is handled at a system level, all of which allow for subsystem 1 and 2 to be able to contribute in the most efficient way towards improving profitability. In the subsystem level optimization, each subsystem was internally trying to optimize and pass along variables, which created a strong design but left room for it to become even better. This slide gives a list of all the parameters used in our model. These are taken from each of the subsystems and compiled for use in the system level model we have built. We will present the mathematical modeling we performed with the use of these parameters, along with the design variables and constraints we selected next.
Next up, we're going to talk about the mathematical modeling. To start, we'll talk about this constraint function. We did a surrogate model for this. And here's just a visual of our heat sink. We're keeping the base area dimensions here the same. And we are changing the height, which is based off D pipe and L fin. Um, and so to do this, we created training data from heat transfer theory that we're going to talk a little bit more in future slides. But we just took various combinations of L fin and D pipe and calculated what the Q allowable would be. And we fit this to a multilinear regression equation. The format's up top here in the first line. The second line is what we ended up getting via Python packages. Pretty handy there. And we just visualized our training data here with our data points in our regression plane. And you can see our data points are not too far off. So that's good that there's no major outliers. And we held back 4 points used for validation. Same process there. And we calculated accuracy based off this formula here, calculate the mean squared error, the mean absolute error, and we get the accuracy value of 97.31%, which shouldn't be too surprising considering all of this is just from heat transfer theory. Converted to a system constraint, we have this Q allowable here, which is just our same equation we got from multilinear regression equation, fit with L fin and D pipe, and then we just transfer this to the negative null form there.
Yeah, using our knowledge of other classes at U of M, we were able to make the following assumptions. Using Fourier's law and Newton's cooling law, we were able to model our system such that it would only require two inputs, L fin and D pipe, in order to backwork the total allowable heat transfer we wanted for our system. And here's a blown up image of our assumed thermal resistance circuit.
And here's our objective function explained. Like I said, the revenue and the cost of carbon emissions are based off L fin and D pipe. Some reasoning in the first two bullet points there. And we put a 5% reduction on the value for the cost of wear and tear due to the surplus in trucks we had available in this fleet in our scenario, and a 5% emphasis on the value of the cost of the carbon emissions due to our company's commitment to lowering that.
Moving on to the optimization method, we chose a recursive ATC algorithm as our optimization method of choice. So we designed the hierarchy pictured here that works to alter the heat sink parameters to prioritize maximizing profit for the company. Essentially, the fin geometry and fluid convection subsystems are optimized based on the results from the previous iteration. Then those values are inputted into the transportation subsystem, where the ATC algorithm adjusts the design variables to maximize profit. The iterations continue until an optimal state is achieved within the boundary conditions. Also, the optimal design variables in each iteration are weighted to prevent one variable from dominating further iterations. As for the execution, we decided to use MATLAB for this. To do this, we set the target profit to be very, very large, essentially making it a maximization problem. Also, each time a new iteration occurs, the values from the previous iteration acted as initial conditions for the next iteration. So, for example, the image here shows the cooling capability, which is fairly insensitive to pipe diameter. So the algorithm would be able to adjust that value away from the subsystem optimal to benefit the profit. As for why we just decided to go this route, this hierarchy format and ATC allows focus on the optimization of one target given multiple interdependent subsystems, which is perfect in our case to maximize profit. So onto the optimization results. The algorithm successfully seemed to adjust the subsystem optimal values out of what they would have done individually to optimize for overall profit while still satisfying constraints and delivering sufficient cooling power. The optimal values achieved are noted here. It was interesting to note that the highlighted values were always high at the beginning of the iterations, but gradually decreased to maximize the system profit as iterations went on. The optimizations seemingly reduced the overall size of the heatsink to just barely deliver the minimum cooling power required to maximize the number of units that fit into one shipment, therefore maximizing profit.
Moving on to post-optimality sensitivity analysis, we ran two sensitivity analyses to test design robustness. Parameter sensitivity perturbs the actual design variables, fin length and pipe diameter slightly above and below their optimized values. For example, changing fin length led to a profit swing from 12.9 million to 14.1 million, a 9.1% change. Pipe diameter showed a 7.3% change. Constraint sensitivity, on the other end, perturbs the bounds of those variables. Since our optimal design hit the lower bounds, we tested what happens if we shift those lower bounds. Losing the bounds improved profit by 9 to 11%, while tightening them reduced feasibility.
Now we'll get into the results. We first wanted to do a reality check on the results from a mechanical standpoint. A small pipe diameter increases both the pressure drop and heat transfer coefficient, but in practice it can cause clogging, require custom manufacturing, and could result in laminar flow, which is less effective for heat transfer. But this trade-off is still reasonable given the low power input to the chip. For the fin length, 4 millimeters is appropriate for compact applications, especially since the total heat dissipation also depends on fin density and spacing, not just length. To validate our results, we recalculated subsystems 1 and 2 using the optimal fin length and pipe diameter from the system level model. Subsystem 1 dissipates about 7 watts through natural convection, and subsystem 2 dissipates 558 watts via fluid cooling. Combined, the system capacity is well over the 250 watt minimum required for safe, steady state operating temperature.
To further sanity check our design, we found various other heat sinks on the market that were similar to our own. Among devices that we found, our device was very much in the middle of operating capacities amongst these. In comparison to the DigiKey heatsink, our design is slightly larger and has a greater cooling capacity. The fins are very similar in length and spacing to this device, which indicates to us that our calculations were well within reason. On the higher end side of heat sinks, we found a high performance liquid cooled heatsink that is just slightly larger than our own. This is similar to our device in that it contains both subsystems that we tested, but additionally makes use of forced convection with a fan and is an all around higher end device. This comes at a trade off of cost, and given our CPU cooling requirements, we believe having a custom sized device in the middle range of cooling capacities makes a lot of sense for us.
When optimized independently, each subsystem selected larger components to maximize its own heat transfer performance. But this approach overlooked crucial transport constraints. In contrast, the system-level optimization, guided by analytical holistic strategy, chose smaller, more balanced component sizes. Despite the downsizing, the system still met its performance goals and delivered strong profitability. This clearly highlights a key insight. While subsystem optimization can lead to locally optimal solutions, only system-level optimization achieves the best overall outcome.
Now we'll go over high-level engineering interpretation of both the key results and the sensitivity analysis. With subsystem-only optimization, we selected larger fin lengths and pipe diameters to maximize heat dissipation. But in reality, we only need to meet the minimum thermal requirement, which we've shown that we can still achieve while maximizing profit. The sensitivity analysis confirmed that fin length and pipe diameter significantly affect profit due to their impact on transport cost. This also reinforces the value of ATC, which enables strategic trade-offs across the system. Some possible next steps for us would be real-world experimentation with this prototype to further validate the model, as well as model improvements, including manufacturability limits, since these affect real-world costs and are not currently included in the profit equation.